All right, hi everyone. I was just informed that there's actually a bug on the submission for the tutorial. It was supposed to be, it's listed as being due at 11:59 a.m., so it's actually past due right now. But don't worry about that. That's just a bug. We typed that in incorrectly. We'll fix that so you submit it. It's due tonight at 11:59 p.m. Not a.m. Actually, can you just email Eric really fast and he'll fix it right now while you're, I think he's not in class, so we'll fix it there. Okay. The tutorial is due tonight, not 2 minutes ago. And to remind everyone that there's a maximum of 2 late days, so you can only use 2 late days. You can't use all 3 as normal, so at most you can submit on Friday night. Homework 5 should be released tonight, not homework 4. Homework 5 should be released tonight. We are also this time going to have one of the recitation sections, and we're going to do it probably this Friday, the same time. We'll record it again, so you can watch it, but it'll be done at the beginning of the homework instead of at the end, so hopefully it'll be helpful from the beginning. And then the feedback on the proposals will be out tomorrow, so we'll send that out to everyone tomorrow. Okay, so today we're going to start by finishing up, or getting into really, resuming the middle of our discussion on PCA. And when we left last time, I described PCA in terms of this loss formulation, right? So we had a hypothesis function that would take our x, multiply it by a thin matrix, and then multiply that by a fat matrix. Those are actually the terms people actually use, a skinny matrix and a fat matrix. But this one here is a matrix that is k by n, and this one is n by k. Okay, so we take our matrix, we compress it down. Or for their vector x, we compress it down. Think of it to k dimensions, and then we inflate it back up to n dimensions. And we are trying to find the u and w that minimize over all u and w this sum. The sum over all our data points of the difference between these two things. So u, w, xi minus xi, the 2 norm squared of that. Right? And I actually wanted to, I did this on the board last time, but I want to actually highlight this a little bit more explicitly now, is that what these things actually correspond to is something like this. So if we have our original points, these are just our points x, they lie in 2-dimensional space here. And I'm assuming that n here is 2 dimensions and k is 1 dimension. So we're taking 2 dimensions, crunching it out into 1 dimension. Also notice that actually this is not like a 0 axis here. The data actually has to be centered. So actually the 0 point is somewhere in the middle here. I'm just drawing those as the directions of the 2 axes. When you multiply by w, that in this case w would be a 1 by 2 matrix. So a row vector essentially. And this would compress down this product here into only 1 dimension. Right? So now this product here is lying in a 1-dimensional space. And if I want then to inflate my data back into the original space, I multiply by u. And what that's doing is that's taking, that really is my whole hypothesis function there. So that's this whole thing here is this product. So this is my hypothesis. And what I'm trying to minimize is over all possible matrices, which essentially correspond to all possible lines in this case. This would, all possible sort of projections onto a line. Which one minimizes the difference between this, which is our hypothesis, and this, which is the original data? And like I said, I'm not going to dwell too much on how you solve this. Because I did sort of promise at the beginning of the course that we would at most get through inversion for matrices, nothing more complex. And here you do have to do something a little bit more complex. So you actually, I should add, you can just take gradients here, right? This is a differentiable function. You could just take gradients of u and w and solve that. And actually, kind of ironically, for a lot of large-scale problems, that is the way people do things. They actually do gradient descent on these two matrices in order to approximate what PCA is doing. I say approximate for the following reason. This term here is not a convex function. Again, all that means for our sake is that it can have local optima. It's actually a little bit one of the cases where, depending on your data, you actually may not have local optima, but we're not going to worry about that. For our sake, it is a non-convex problem. That means that if you do gradient descent, you might hit a local optima. But it happens to be one of these few problems that you actually can solve globally, even though it has local optima. So it's sort of an amazing thing. But it's based upon either, you can phrase it in terms of either, they're very related, of course, a singular value decomposition or a eigenvalue decomposition of a certain matrix. And so you can do this by essentially taking your input data, and I'm going to, again, if this makes sense to people, that's great, or if this sort of seems reasonable, that's great. If it doesn't, don't worry about it. But you take your input data, we're not going to require you to implement this, let alone prove it or anything like that. You can just run this call in Python, so we're not going to worry too much about it. But for those who may have sort of heard about this before, we take our input data matrix, which is, again, a matrix of all data points as rows of that matrix, and we compute what's called the singular value decomposition of this, which is a decomposition of that matrix into the product of three matrices, where these two matrices, U and V, are what are called orthogonal matrices. That means that U transpose U equals the identity, and V transpose V equals the identity. So they are what are called orthogonal matrices, and S is diagonal. And it turns out that, for reasons I won't go into, this actually provides a solution. Essentially, this matrix V ends up being the W matrix. And if you want W to have only k columns, you just take the first k columns of V. So W here ends up being equal to V. And I'll write it like this, all the rows and 1 through k columns. Now, one point I'll make here, and this actually is, again, just an aside, but maybe sometimes it's somewhat interesting, is that there's actually no unique solution to this problem, right? Because if I have some U and W that is my optimal solution, this is also equal to U, any other matrix A, times A inverse times W. In other words, I can actually rotate or sort of scale these, right? Because this term is just equal to I. And so I can make a new sort of U tilde and a new W tilde that is still the same when you think about projecting onto the space here, right? And what that corresponds to actually is just taking this dimension here, this sort of dimension here, and just kind of rotating it in space, and then undoing that, rotating and stretching, applying a linear transformation, rotating and stretching this thing in space, and then undoing that in your U matrix. So it's exactly the same. It's hard to actually imagine that in 1D, because in 1D you really only have, the one thing you could do is you could have it be negative, right? You could actually have it go the opposite way. That would be fine too. But my only point is that U and W here are not unique, though their product actually is unique, it turns out. That's also not obvious, but it turns out that their product is unique. But where this sort of comes up is I could actually put S, this matrix S, I could put it into sort of V if I wanted to or not. You just have to then pick a U such that you sort of undo the transformation. And U actually here ends up being the matrix U. This is transposed because W is a fat matrix. Sorry, I had this wrong. This is bigger than this term. And U here ends up being V 1 through K times S 1 to K 1 to k inverse. And I could actually move that S term to this one or before there, doesn't really matter. But again, why that is the case actually comes out very nicely from what a singular value decomposition is, and the fact that an eigenvalue problem, which is very related to the singular value decomposition, is actually minimizing a certain function, which is actually almost exactly that function. But I don't want to get into that because I think it requires a little bit of rigor there that I'd rather not get into. The only point that's relevant here is that despite the fact that this problem does not seem like it should be solvable, you actually can solve it with, on the order of a few lines of code. Again, sort of magical code, because the actual only thing that really happens here is you just call SVD after transforming your matrices in the proper way. So I'm not going to worry about that too much, but just know that you can solve this very easily. And here you can certainly use, scikit-learn also will give you the exact same results. I believe on the, I forget if we left the PCA question in or not. If we make you do PCA on the homework, we will let you use scikit-learn. We will not make you copy those lines of code yourself. Any questions? Yeah, we'll get into that actually. Maybe I'll show an example in a second right now, actually. So let me I'm going to come back to this point here, this WX point. The fact that I can take my original data, say an example I, right, and I can apply my matrix W to it. Now, I know that this product has all the information I'm going to be able to get in my reconstructed version, right? Because if I multiply with something else, I can't add new information to that. I am preserving all the information I have that I keep about that vector in this product, right? So this product is a vector in Rk. And for k less than n, well, less than really, it's equal, it's not very interesting. If k is less than n, this is kind of an interesting thing. Because what we're doing in some sense is we are finding a projection of the data that tries to make the data as close as possible, tries to preserve as much information as possible about that original data, because when I reproject back or rescale back into my original dimensions, I want it to be as close as possible to my original data points, right? And the way you do that is you preserve as much information as possible about the underlying data. So if I projected on this dimension, for example, right, along this dimension, that would not be very good, right? Because that throws away a lot of information. My sort of reconstruction would be something like this, all the points are bunched along this line here. And so that would not be a very good reconstruction. So what that means in practice, though, is that PCA is very nice when it comes to understanding your data in a lower dimensional space. Right? So if I have MNIST, for example, which I'll see in a second, that has 784 dimensions, right? That's not something we can visualize. We can't visualize what that looks like in 784 dimensional space. We can plot single examples, we can plot images, right? But we can't really view an image as a point in 784 dimensional space. That is well beyond us. I think we're maxed out maybe at probably 2. 3 we're okay at, and then 4 we're slightly okay at, and then 5 we can't do it all. So what this means is that if we run PCA and say set k equals to 2, so if we run PCA with k equal to 2, and then we plot w times x, I, this is going to be giving us a 2-dimensional representation of what our data looks like. So here's what it looks like on MNIST. And I actually realized I didn't actually label what these points are, but each color here is a different image. Sorry, a different class, a different label. In other words, each color here is either the digit 1, 2, 3, 4, up to 9, 0 up to 9. So this, I'm actually not even drawing them all. It's like I think 10,000 of them. 60,000 just gets more messy here. But more than sort of any actual kind of specific feature of this graph, the important point here really is what the characteristic of what I'm actually showing here. So what I did, again, from a high level, I took the digits of MNIST, I normalized them so they made them have 0 mean and standard variance, and then I ran a PCA to extract the top 2 principal components. And then I plotted these 2 principal components for every point where I color code the points by what digit they represent, right? And so what you see is that, first of all, it's not like these things separate nicely into 10 different clusters. And so it's really just living in some 2-dimensional space here and a 2-dimensional linear space here, and we can get perfect separation in that case. If you try to use these to classify the digits, for example, you would imagine you do much worse than if you use all the dimensions. I mean, you did it for the homework. You get like 92% accuracy when you use a linear classifier in all the dimensions. If you do it here, you'll get like, I actually don't even know, probably 60 or 40 or something like that. I mean, there's just plenty of overlap, right? You can't separate the yellow guys from everything else with a linear classifier here. So what this is saying is that you are definitely losing some information when you go to somehow the plot I had next got lost. Huh. I'll try to draw it. I have a plot of the singular values too, but we'll just talk about this for now. So some information is being lost when you actually when you do this, but it also says something interesting, that there is some preservation of structure here, right? It's not like this is a random collection of points that's spaced randomly where the colors have no relationship to each other. This color here, which I'll just say is like a 2. Let's say the red is equal to a, well, it probably actually is a 0. So say the red is equal to a 0. Because I think it goes from 0 to blue. 0 to blue. I think 0 is red and blue is, or the other way around. I don't know. Let's say this is 0, and these are over here, or the orange next to it is 1 or something like that. What it's saying is that even when I project down to just 2 dimensions, I can distinguish pretty well between these orange guys here and the red guys here, right? So 0s and 1s, even in 1 dimension or 2 dimensions, look pretty different. And that sort of same statement holds more or less for other digits as well, other sort of separations between different digits. So the other thing we can visualize, and I don't see this figure actually. I thought I had put this in. I have this figure. But the other thing I'll say is that the loss here, remember the loss is given by, well, the loss really is the sum. Loss is this term here, right? It turns out actually that loss can actually also be computed from the single value decomposition without having to actually compute the loss directly. You actually ends up being a function of these S terms. Again, we're not going to worry about why that's the case, but it is the case. And so it's also a good idea to plot the loss over the number of components. So this is going to be a plot of loss and then the number of principal components. And this is a similar question now to the question of how many clusters do we use in k-means, for example, right? How many principal components do we take? What's a good number? And a good way to think about this is by using the loss functions. The loss looks something like this. Something like that, hopefully. If you're really lucky, it'll look like this, right? It'll look like this, something like that. But most of the time, it looks something more like this. And the question of how many components you take now can be done by looking at essentially how much loss in your reconstruction do you want to tolerate, right? And you can also think of the loss in terms of, maybe I'll divide the loss by the total magnitude, of if I pick 1 singular value or 0 of them, what would my loss be then? You could think of picking some threshold where I represent, 90% of my data. I have, 90% of my data is being captured by a certain threshold. But it really is kind of arbitrary, just like it is for k-means. So just like for k-means, there's no real way, there's no good, for example, cross-validation scheme you can really use here because, again, it'll work better on the training data and testing data. It'll just always sort of be better. It isn't this kind of thing where you you have like a training and testing loss where you can really think about overfitting. For the most part, you end up just doing worse. It ends up doing better and better on all testing and training as you have more components. But these sort of plots give you some sense of how you might choose how many principal components to take. And so that's the sort of, again, magic of picking how many principal components you use. The reality is, just like number of clusters, there isn't a true answer here. And so it's not a great idea to, I mean, you can pick some, you have to pick one, but there isn't a really kind of clear-cut way of picking that number. Question?
So I know that PCA is good for visualizing high-dimensional data.
Yep, like this.
Understand what you're visualizing if you don't know what the axis is.
Yeah. So the question was, PCA I've heard is good for visualizing high-dimensional data. And in fact, I showed you how good it is, right? It's just, look how good it is for visualizing that data. So this is actually an interesting question because it is great for making these graphs. But at the same time, what does this graph mean?
It's not necessarily good because it's not telling you, like it's not showing any clusters of the labels. Right?
Correct. I mean, it's showing you, so I would actually argue it's showing you something. It's showing you that there are some separations. So all these orange points here, which I believe are ones. One is a very distinct digit from all the others. It doesn't have any curves, right? It's sort of always is kind of similar. I believe these are ones here. It is showing you something, right? Like the ones are kind of similar. If they're far away from the red ones, there's something like that. So if I only had two classes, it would look more separated in some cases, right? So we're just telling you something. But it's also very important to know that there are no units to be had here, right? Even if you have features that actually have units in their native space, and I guess you kind of do here, they're all pixels, but there's no great notion of units. Especially if you have different, you have features that are different units. When you do this, right, W here is a matrix that usually is dense. And so what you're doing here, right, is I'm saying that, the ith component of this guy, right, or the jth component here, right, is equal to, the jth row of W. That would be this guy here. That would be equal to the jth row of W times X. Sorry for overwriting past stuff. I hope I'm somewhat reasonable. I'll just write it down here. So in your transformed data, you take your W matrix, you take the jth row of it, and you multiply it by X. What this means is that I'm taking some linear combination of all my original features to create some new dimension, right? To create some new data point, new coordinate here, which does not really have any physical meaning. There's usually no real interpretability to these things. It's just some axis now. I don't put labels here very intentionally because they don't really have labels. So what this means is that it can be very good at kind of visualizing some amount of separation. And I should be clear also, this is linear, visualizing linear separation. So you can actually, if you use nonlinear dimensionality reduction, you can which we may talk about later in the class. We'll see if we have time. There's some nicer kind of visual ways of doing dimensionality reduction. PCA is a linear one. But with all of them, really, there's not going to be a great definition of what these axes really mean because they are just linear combinations of existing. In the case of PCA, at least, they're just linear combinations of the features. So it's great. You can do it. But the value comes more from just sort of seeing if there is separation, seeing if there is distinction between classes here, or seeing if there's some clustering of data, right? If I had no labels at all here, I wouldn't really know how to interpret that. I would just see there's a big kind of smeared out form where you have more points, a little denser here and a little sparser there. So I think people sometimes overstate the value of PCA. It's great for, or at least for visualization. It can be great for first checking things, but I've never seen really compelling examples in the real world where somehow you run PCA and all of a sudden this amazing pattern just pops out of your data and you know exactly how to interpret it. That's a rare occasion. Yeah. Is U is the so okay, W is the eigenvectors of X transpose X. And you can actually see that because the singular value decomposition, the right singular values are just they are the eigenvectors of this equation, in fact. And so they end up being the eigenvectors of this thing, of x transpose x. Yeah.
Can you just plot like the variables along the data used to like find some patterns or like some correlations?
So the question is, can you plot the data points along with the axis? I'm not sure. I don't think I understand.
The variables like the loadings, so you plot them as vectors, like the biplot.
The loadings you plot them. I'm not seeing what you're saying. I am plotting the labels here.
Oh, okay. No,
The colors are the labels, right? The colors are what digit it is.
I was just wondering for you're putting here the data points.
I'm plotting the transform data. So I'm plotting here W times X, where W has 2 rows to it. So I'm plotting the first 2. Yeah, it's important. I'm not plotting here the principal components. I'm plotting the product of W times X. I'm plotting the transformed data in 2 dimensions. I can also, by the way, plot the columns of W. And the columns of W, sorry, the rows of W, actually. And the rows of W actually live in the same dimensional space as the original data, right? And so it's kind of interesting how this actually looks here. This looks like the following. This is what the 50th principal components for MNIST look like. So again, what these are is if I take W and I take the first row of W, and I think of that as the vector in the same space as as my original data, then this is going to be essentially my. Actually, I'm actually plotting here the. Doesn't matter actually because they're the same to a scaling. So here I'm. Yeah, you can think of it as plotting the rows of W, or you can think of this also as plotting a scaled version of the columns of U. Okay. They are in fact the same thing by our formula there. One's just scaled by the other, and scaling is kind of arbitrary, so it doesn't really matter. Okay, so what is this showing here? This is showing that every digit, when I reconstruct it, when I create my hypothesis, what I'm actually doing here is I'm creating a linear combination of these images and representing my digit in that way. So what it's saying here, remember, one way to think about my final output, right, is I take some vector. This is now a vector in RK. And so I'm plotting the columns of U here. And so what that means essentially is that I am plotting, our final approximation, I'll call it x tilde, is going to be equal to U times this thing, right? So that means that this is going to be a linear combination of this column and this column and this column, et cetera, right? Where there's only k of them. And so what we're seeing here is we're seeing, going across this way, we are seeing the top principal components. That means if I represent my data using 5 principal components, then I'm going to represent my data as every example as some linear combination of that first image up there, second image, third image, into the 5th one. So every image that I have is essentially going to be some linear combination, some coefficient times that first image plus some other coefficient times the second image, et cetera, right? So this is another good way to sort of see what PCA is doing. And one common feature of PCA I should add is that you very quickly start getting things that look like this, right? So they actually become uninterpretable pretty fast. The first few you can kind of see a 0 there, maybe a 7 and a 3, right? You can kind of see that there's some images there that are capturing something about real digits. But very quickly they become kind of incomprehensible to people, and you have stuff like this. That just isn't that useful, and we sort of see a lot of noise in it. And the way you create the digits really is by finding the exact right combination of that seeming noise to reconstruct what the original image actually looked like. So this is a good plot to look at, but it also, other than the first few principal components, there isn't usually that much value in visualizing what these things really look like. Yeah.
the first 10 components are crucial, but then they're not?
Well, yeah, so this is one plot that's good to look at. The other plot I will say to look at, so this is a plot of the actual components, right? The components in U, essentially. The columns of U, or two of almost essentially the same thing, the rows in V, right? They're just scaled. One's just a scaled version of the other. What's also good to look at is how well these things actually reconstruct the data, or a data point, right? So if I also, before I was plotting, this, right? I can also take my entire transformation and plot my transformed data, right? I take a data point, I plug it into my hypothesis, and plot what it looks like. That would be kind of this figure going back, right? That's kind of this one. And that's actually a pretty reasonable way of saying, how close to my original data am I? Now, of course, in general, you can't, plot it again in the 784-dimensional space, but I can take one image, apply PCA, and see what it actually looks like, right? So this is what this looks like. And again, what I'm going to do here is I'm going to vary my k. So I'm going to vary the number of components that I select here. So this is so these are my original digits, and I'm going to keep flipping back to this. Well, I will keep flipping back to this page, because this sort of shows what digits they actually are. And here is the reconstructed images if I take two components and reconstruct them. So this is actually a view of what those data points in that two-dimensional space looked like in their reconstruction. And you can see why it was such a mess in some sense, right? That I can kind of picture what some of these things are. Again, not really. Which ones can I do? Zeros. The zeros I can do really well, right? This one here. That looks like a zero still. And in fact, actually, if you also look, and again, this is getting maybe a little bit specific here, but the first principal component really highlights the zero pattern, right? That's what it actually highlights. And so this is why I believe this to be a 0 and a 1 here, this slide, because I know the first principal component actually distinguishes between 0 and 1s. So I'm guessing those are either 1s or 0s, and this is either the opposite of those, whatever it is. That's still a guess, but I think I have a good reason to believe that. So here's for 2. Here is for 10 principal components. And it's getting better. But what's interesting here is it still isn't great, right? There's still plenty of digits where I can't really tell. Like, this is a 4 here. I can't really tell. I mean, maybe you can kind of squint your eyes and see, but I could easily get it wrong. This is a 9 here. I would definitely not get that from this, right? So they're not great, but they're getting better. And as we go higher and higher, of course, it will get better. So by the time I take 100 principal components, I can basically tell what all the digits actually are. What's interesting here is that this took many, many more principal components than were actually visually recognizable, right? So it is, in fact, taking some odd, weird linear combinations of these very highly variable images to reconstruct exactly what this looks like. Okay, so just because we know we can't interpret what these things mean doesn't mean they aren't important. They're actually very important for reconstructing the image. But what this also says, and this is the last point I'm going to make here, this was asked a little bit last time. What this also says is that, look, I can visually look at my data after this transformation, and I would bet I can classify it as well as I can classify the original images, right? I think I'm going to get the exact same labels. Maybe this one's a little bit tricky here, but for the most part, maybe you take 200, right? Our original data is 784 dimensional, right? What I'm saying here is that I can look at the data myself when it's been reduced to only 100 dimensions and do just as well. And so that is actually very good evidence that you don't really need all 100 dimensions in your, all 784 dimensions in your data, right? You can kind of make do with only this many. But it's really important kind of what my criterion there is for saying you could make do with it. My criteria there is saying that I can recognize it. And this is a point that I've made before, and I kind of want to make again in machine learning, and I'll, I think, make it a few more times as we talk about some examples. But machine learning tasks almost always, I mean, there are examples of superhuman machine learning capabilities, right? Things that do better than humans. But almost always, if you can't do something, if you can't do a task, the computer can't either. And so when you're trying to pick, how many dimensions should I use, you could do it from that weird loss way. But a better way to do it, if it's possible, is to actually plot your data that's been reduced and say, can I still accomplish the task that I'm trying to make the computer do? And here I would say yes, and here I would say no. So this is actually a good criteria for how you pick k, right? Do I pick k to be 10? Probably not. Maybe I pick it to be 100. And so the best way to sort of pick what k should be for PCA at least, if it's possible. It's not always possible to visualize the data at all, so maybe you can't do that. But if I can visualize it, if I can visualize just the reconstructed data in some way and label it myself, that's a great way of picking how big k should be. Okay, so here's the last point I'll say. In this lecture, we really talked about PCA and k-means as kind of, they are unsupervised learning algorithms, right? And the point was, in some sense, to extract some structure from our data. In the case of k-means, and they're actually surprisingly similar, these two algorithms, right? In the case of k-means, the structure we're extracting was means from the data. So we're trying to find k different centers, such that every point was close to at least one of those centers. In PCA, we were trying to find a kind of a reduced dimensionality subspace, where if we project the points into that subspace, we don't lose too much information. Okay? And so that's how we kind of set this up. But the other point I'll make is that PCA and k-means are incredibly useful algorithms for supervised learning too, as methods for data preparation and supervised learning. So it is extremely common, for example, when you have a supervised task with a lot of examples, to first run PCA on the task to reduce the dimension. Like with MNIST, right? Most times, if you want to apply a classifier to MNIST, I guess it's small enough now that we don't worry about it, but it was very common for a long time before you wanted to ever try a task in MNIST, is you would first reduce the dimensionality by running PCA with, say, 100 principal components. That's how you'd apply and then you'd apply your algorithm. Now I should add that if you use a linear classifier to classify digits, you're not gaining any representational power by doing that. You're just reducing the dimensionality of your space, and so it might work better, or it might not. It only will work better if you're sort of overfitting in your original space, but we won't worry too much about that. But the point being that it is very common to reduce the number of features you have by first applying PCA to your data. The best use of k-means in supervised learning, I think, and this one's a little less common, but I mentioned it before, and I'll mention it again because it is incredibly useful, is that you run k-means on your data to extract k different centers, and then you create radial basis functions around your data using those centers. So before I describe this as sort of the way you'd find your centers for RBFs is you just pick points randomly from your space. That kind of can sometimes work okay. This usually works much better though. As you might imagine, because these centers, at least ideally, are much more spread out across your data, so they sort of capture your data better. This is an incredibly useful transformation to do, to use a nonlinear classifier on your data, because it really can vastly sort of, it's an easy way of allowing for nonlinear classification of your data, right? So, and you can use the same median trick to pick the bandwidth there as a median of all pairwise distances between the centers, and it works really well kind of as a first quick check for a lot of algorithms. So the high level point here though is that while these things are useful in their own right, they are just as often useful as data processing steps for some larger tool chain. The number of times actually where you can just cluster your data and get some amazing insight from that clustering or from the PCA analysis. It does happen occasionally, but it's extremely rare. You will almost never just be able to run k-means on your data set and just see, oh look, my centers show that I have two distinct clusters in my data that are completely different, and that solves my problem. I've gotten the insight that I need. That's very rare. Again, it might happen, but usually you never get that. Usually you cluster things and you sort of see things that are kind of a mess of different all sorts of different examples, and you run PCA and you see something like this. You very rarely get like a beautiful picture that just separates things out beautifully. However, these algorithms are still very useful as pre-processing steps within a larger supervised pipeline. Okay, any questions before I move on to the next lecture? Yeah. So the question was, how do I compare something like autoencoding with using k-means? We haven't talked about sort of autoencoders or neural nets yet. So I don't want to give too detailed an answer here. The comparison of clustering algorithms or unsupervised algorithms in general is very difficult because they are minimizing their loss function by definition. And that loss function is somewhat arbitrary, right? You don't really have a true answer. I don't know how many clusters there are. And so the way algorithms are compared is in a very ad hoc manner. You know, if I reproject my data, does it look good? If I plot it in 2 dimensions, does it look separated or not? People sort of evaluate it and things like that. But then oftentimes, you know, the best algorithm will be the one that minimizes exactly the thing that they're measuring. So they'll measure like separation in 2D space. And so of course, some other algorithm that you designed to minimize that is going to do better on that objective. So what I'll say is there's no great answer to that. Now, autoencoders, as you're using them, are essentially a generalization of PCA because they actually can capture everything PCA does, but they also have nonlinearities. They can do better too. So typically that will give you better separation and better sort of identification of reduced dimension subspaces. But again, it's all kind of ad hoc because you don't really know if you don't have a true loss function, it's hard to compare. So here we had an easy answer. Just it's the reconstruction error, which you actually can use to compare, but that's not always the thing people really care about. Yeah.
Let's say you have a model, but you use PCA first and process data.
Yep.
Would you just use the data that explains all the variance? Like for example, for nest, you say the first 100 components are the ones that represent the variance of the entire data. Then would you just build the model with those, like with the data that has those like 100 components?
Yeah. So I think the question was about again, how do you pick the number of components? Do you pick it about? So explaining data and loss are the exact same thing. One's just a ratio of the other. So you can pick it based upon loss, but as I said, don't do that. Pick it based upon what's something that's some better analysis. I mean, that's exactly just this figure here. So you can pick it based upon where you see some curve kink there, but that doesn't always happen. If you have a supervised task, you can pick it with cross-validation too. So you can cross-validate the number of components you pick if you have some supervised tasks that you really care about. That will work too. Okay, so we're going to shift gears now a little bit and talk about anomaly detection. Though really this is a very sort of simple lecture when it comes to anomaly detection. I'm more than anything going to talk about density estimation and probability again, under the guise of anomaly detection. And it's actually fun. We're not going to get through this all today, but we will get through some. And I don't think we need a whole lecture on recommender systems, so I'm going to abbreviate the next lecture. We will have a whole lecture on deep learning, though, so that one we will not abbreviate. Okay, so I want to start by talking about anomalies and outliers and what I mean by that, because actually anomaly detection is kind of a loaded term, and then it can mean a lot of things to different people. Then I'm going to talk about 2 main things here. And the 2 main topics I'm going to talk about here are multivariate Gaussians, so the multivariate Gaussian distribution, and a model called the mixture of Gaussians, which is a very common model, and we'll talk about what that means and also how we can model data that is drawn from multiple Gaussians. We talked about Gaussians already a little bit, but what we're going to cover here, which we only covered in one slide before, so we'll do it in some more detail, is Gaussian distributions over many dimensions as opposed to just over one dimension. But I'll talk about how this relates also to outlier detection and what I mean by anomaly detection and outlier detection for this lecture. All right, here are our announcements. Okay, so when we talk about a domain like anomaly detection, and I should clarify, I think some people would even disagree that this lecture is all about anomaly detection. I think they would clarify that it's, they think it's much more about sort of these issues and how you treat different types of anomalies in different ways. But I'll start this just by saying, what is an anomaly? Anomaly detection is a sort of a natural thing, and I'm just going to use this kind of for its intuitive meaning. If I have some big data set, say my data represents, the cars that were manufactured, right, and some specs on the cars that have been manufactured by a certain manufacturer. It seems very natural that I want to say, what are the anomalies in this data? What are instances? What's a car that just somehow its specs are just far off from anything else? That's probably a bad thing, right? Anomalies tend to be bad things. I mean, so we sort of associate them with bad things. When you have a bunch of data and there's a couple points that just do not seem like any other point in the data set, that typically is seen to be a bad thing, right? Or at least something that's worth investigating more. If you're analyzing banking data, then your anomalies may be fraudulent transactions, right? Because most transactions are not fraudulent; they're valid transactions. But all of a sudden, you have some transactions that just look so strange they end up being fraudulent. And this is kind of the holy grail, actually, for a lot of data science is anomaly detection, right? We want to take a massive data set and somehow find those examples in this data set that are wrong, where wrong here is entirely dependent on the actual domain we're talking about. It may or may not be what a machine learning algorithm finds, but wrong to the people doing the domains, to people participating in the domain, is sort of very naturally defined. Like, is this transaction fraudulent or not? And so in this view, anomalies essentially are, to put it kind of informally, they are weird data points in your data. They're things that don't really fit. And there's some notion of which those should be important. We should look at those to try to figure out something that we might do. And so there's sort of two views of anomaly detection that I want to highlight here. There's the supervised view, which basically treats it like a supervised learning problem, right? We have a bunch of data points. We label some as anomalies, and we build a classifier that can classify the anomalies, what's anomalous and what's not anomalous. Right? So if we have a bunch of financial transaction data, and we go through it all and we label every point as being either non-fraudulent or fraudulent, then we're sort of all set, right? We can just treat this as a supervised learning problem, and we sort of know what we're doing. On the full other extreme, there's the fully unsupervised view, which is to say that anomalies essentially are just outliers in the data. Right? And the nice thing about the term outlier is that term doesn't actually require any notion of the actual task at hand. And so it can actually be determined by an unsupervised algorithm. So if I have some data points here, and well, let's do this. If I have some data points here, just erase that. I don't know what I was drawing there. I was trying to draw it in 1D, but that's silly. So I have a bunch of data points in 2D. Right, and I have one point out here. This is an outlier, right? And the way we define it as an outlier is we build some distribution that captures those points, and we see that the probability here of this point is very low compared to the probability of the other points. In other words, this point is an unusual occurrence based upon these. So in our notation here, and I'll have a separate slide on this, but we will consider outliers to just be points that have a low probability, where I'm not specifying what low is. I'm not setting a threshold on what low is, because oftentimes you don't care about the absolute probability or absolute density. What you actually care about is just, of your data set, what are the most unlikely data points, right? So we are going to focus on the second version here. We're kind of in the unsupervised learning setting. We're going to focus on the second one of detecting outliers in data and thinking of anomaly detection really as outlier detection. Now, what you really probably want to do in practice is some combination of these two things, right? I probably do not want to take every single financial transaction as a bank and label it as fraudulent or not, because there are many, probably hundreds of thousands of those a second, and maybe more in the world. I have no idea actually how many there are in the world. Even for a big bank, it's probably going to be a lot per second. You probably don't want to do that. You don't want to have someone sitting there labeling transactions, because they won't even know what they are at that point. They won't even look very closely at them. The whole point of these things is to be able to avoid someone manually looking at these things. And so even collecting a big enough data set could be very hard here. But you probably don't want, so you probably don't want to label all the transactions, but maybe you want to label a small subset of them, right? Where you just, I take some handful of my transactions and I want to label those. And that's all well and good too, but if I just label, say, the fraudulent ones, then I'm going to have a very imbalanced data set. A data set does not really capture the true underlying distributions here. And so in practice, you probably want to do some combination of the two, where I use all my data to kind of build some sort of distribution over my inputs, and then use some limited amount of labeling to actually label, certain regions of that space as being either fraudulent or not fraudulent. So that's very high level there, but and we're not going to cover kind of those ideas, but just know that from a high level here, you probably want some combination of supervised and unsupervised learning to do real anomaly detection, but we're just focusing on the unsupervised part. We're going to think of it just as finding outliers in your data. And by the way, that's not at all ideal, right? Because your biggest customer as a bank will probably always be an outlier, right? They're transacting more money. That does not mean they're actually fraudulent, right? So while anomalies are usually outliers, the converse does not hold. Outliers are not always anomalies. So just high level things to keep in mind. We're going to quickly ignore all this and focus just on outliers here and take the unsupervised view and just call anomalies outliers. So again, outliers here, for the sake of this lecture, are just going to be points of low probability. So they are just points that when we build a model of the data, P of x for those points, so we're building a model, we're taking all these points here. We take the outliers too. We take all the points, we build some model, P of x, say parameterized by some parameters, theta. And then I can evaluate the probability of, under this model, of all the data points. And the ones that have the lowest probability, those are the ones that are most likely to be outliers, right? And this is really, again, because we're doing it just based upon the data points themselves, this is really an unsupervised learning algorithm, right? We're talking about just having x as our input here. And what we're going to do is we're going to build a model of x. Now, we actually could formulate this in terms of hypotheses and loss function, all this kind of stuff, but I'm actually going to adopt more the notation from the probability lecture here, because this is really going to be more about building distributions of my data, and then using those distributions to identify which points are the outliers. So I'm going to mainly be using the notation of probability, not of loss functions and hypotheses, though in the same way that supervised learning algorithms had this nice sort of match between maximum likelihood estimation and a lot of algorithms, you actually can formulate these all in terms of hypotheses and loss functions as well. And later we'll actually see a very close connection between the one that we're going to describe, which is a mixture of Gaussians, and the k-means algorithm. They end up actually being very similar in a lot of ways. All right, so let's talk about multivariate Gaussians. Who here has seen multivariate Gaussians before? Okay, so this is probably going to be a review for everyone, or not for everyone. For anyone who's seen it before, this is going to be a review, but hopefully still, for those that haven't seen it, still interesting. Maybe if you've seen it before, interesting too. Okay, so we've seen single variate Gaussians, and I'm going to go through this fairly quickly. We've seen single variate Gaussians before. So they were random variables where the probability density of that variable had this form, which was the probability density of a Gaussian or of a normal distribution. And it's shaped like this, right? It's shaped like a bell curve. So the density function here, which is a function of x, here looks something like this, where this high point was at the mean mu, and some notion of this separation here. I shouldn't write it there. Some notion of how spread out this was given by sigma, or sigma squared. Actually, I always wrote it in terms of. A multivariate Gaussian is just the multidimensional generalization of this. So we're going to actually now think of x, rather than being scalar valued, as being vector valued. And we're going to think of it as, so it takes on values in Rn. And it has the following density given by this thing. where, again, this thing is sort of, it isn't too crucial what this actually is. This is essentially a, well, for the sake of our say, all we're going to say is this term here is a normalizing constant. It just makes the whole thing integrate to 1. And this term here looks a lot like a distance function, right? Where points that are farther from mu, the parameter mu, as measured by this matrix sigma inverse, those points have higher value here. When you exponentiate, you're taking the negative exponential of a big thing, and so they'll have very low probability. So the big idea of Gaussians, and we'll talk about this in a second, I'll give some intuition about this, is that this is a density function where points when x is very far from mu, and this is big, and I'll sort of write it like this, but of course really for a Gaussian it's x minus mu transpose q. Sigma inverse, x minus mu. When this thing is big, that means the probability is small. This thing, big, p of x is small. So when I'm very far away from mu, as with the Gaussian, right? With the Gaussian, when I'm far away from my mean, I have very small probability. Here, when I'm far away from my mean as measured sort of in a higher dimensional distance, I have small probability there too. Is a question there? Yeah, so I'm not really writing it here yet. We'll talk about what they are in a second on the next slide. Here, sigma and mu are just going to be parameters of the distribution. So you remember that every distribution we had some parameters, right? It had some numbers that characterized it. So a Gaussian has what we call a mean and a variance, mu and sigma squared. Here we have mu and big sigma, where big sigma is also a parameter. We'll talk about what it means in a second. But really, so far, they're just parameters of the distribution. They're just numbers. I mean, here, mu is a vector in Rn, sigma is a matrix in n by n. Actually, has to also be symmetric. But they're just number, or they're just vector valued parameters or matrix valued parameters for now, until the next slide. We write this in a few ways, so I'm going to use a little notation here. That's a total pain to write every time. So I'm going to instead write the p of x, given these things, mu and sigma. The Gaussian version of this, I'm going to write like this. Script n for normal with mean mu and covariance sigma. And I will also write, remember, in our notation for random variables, x here's a random variable. When we write little x, we mean a particular value of x, right? Whereas big X means the random variable itself. And so this means that the probability of any specific x is equal to this thing as is defined. We will also sometimes write this being a little bit ambiguous here, but not really. We'll say the big X is distributed as a random variable, a normal random variable with mean mu and covariance sigma. So this thing here just means sort of defines the distribution. This thing there, when I include the x, actually means the density of that distribution. You'll see both of those a lot in practice, so I'm going to use both of those, but just know that they mean subtly, slightly different things. Oh, and this bar here denotes the determinant of a matrix. That is equal to the product of its eigenvalues, for those that have seen that before, but not too important. It's just a constant that lets this thing integrate to 1. Yeah? Yeah. Yeah, so if this term is big, did that part make sense? That when this term is big, the probability is small. Right? If this term is small, so let's say that actually x equals mu. Right? Then this thing is going to be equal to 0. And that means the probability will be big. P of x is big. Right? Because no matter what you pick for x, this term here stays the same, so we ignore that. That doesn't change the relative scalings of the different points. But if x is very far from mu, and then this thing is actually big, then that ends up making the probability here, you take negative exponential of that, and that makes the probability very small. Whereas if this thing is equal to it or very close to it, then the thing inside the exponent is negative of a small number, and that'll lead to a larger probability. Okay, now, although those parameters, as they're stated there, could just be thought of as general parameters, you never think of them that way, because they have very nice properties that relate those parameters to properties of the distribution. And in particular, this is completely non-obvious, by the way, that these integrals actually integrate to that. These are high-dimensional integrals over all of Rn. But you'll have to trust me on this, that when I take the expectation of the random variable x, in other words, if I integrate over all space x times its density, I will actually get, and that's integrating over all of Rn, right? So I'm integrating, not just integrating like this, but actually integrating over all of Rn. I will get the mean value, the expected value of my random variable, actually going to be equal to mu. So mu is really, and it's called, and it always is in fact, the mean of the distribution. That means if I sample a bunch of points from this distribution and I average them, their mean is going to be approximate. Those averages is going to be approximately equal to the mean there. What sigma is the covariance matrix of this random variable. And that's actually a very important quantity there, which we'll look at graphically in a second. We talked about variance before. So for a single random variable, you remember that the variance of random variable x was equal to the expectation of x minus its mean squared, right? And the covariance of two variables, the covariance between two variables, between x and y, was equal to the expectation of x minus the mean, or I'll write it like the mean of x, times y minus the expected value of y. Right? That was equal to the covariance. This one here is, of course, always positive, because that term in the middle is always positive. This one can be positive or negative, because there's no need for one to be positive, and one can always be positive, one can always be negative. So that is the variance and the covariance. What sigma actually is sigma is actually a matrix of all pairwise covariances and variance of every variable in that vector. So remember, our vector x here, this is getting more like grindy and grindy every day. So our vector x here, has n different components, x1, x2, xn. And what sigma ij is sigma ij is actually the covariance between xi and xj. Thinking of these terms as being themselves, each element of the matrix as being a random variable. And the covariance of a variable in itself is just the variance, right? If I plug in x to both these sides here, I just have this term squared. So the diagonal elements of this matrix are the variances, the univariate variances of the variable, whereas the off-diagonal elements are the covariances between different variables here. And that's really what those things are, more fundamentally. So one variance property here is how you go about creating random variables. So we all know, presumably, how to sample a random variable from a... we all know how to sample a random variable from a... Well, we don't maybe know how to do it procedurally, but we all know how to type in Python np.random.randn, and you can sample variables from of a univariate random, normal random variable, right? That's really interesting how that thing works. It's actually kind of cool how it works if you want to look it up someday. But we know how to create random variables from a univariate random variable. How do we actually go about creating samples even from a multivariate Gaussian? This is actually both instructive not just in terms of sampling from it, but it's also very useful to think about kind of what these things mean. So if I have a vector x in Rn, a random variable x, which will take values on in Rn, and this thing I know it to be Gaussian. Probably shouldn't write it like that. Whatever. X is Gaussian with mean 0 and the identity covariance. That, by the way, because the identity is the covariance, that means they're all independent. There's no correlation between the different variables, and each one essentially is a random, standard random normal variable. So this just means that each xi is normal with mean 0 and covariance 1. Sorry, variance 1. And they are all independent. So if I have a random variable like that, and I take some matrix A, so A, and I'll just think of it actually, for simplicity, I'll just think of it as n by n. It can be other shapes too, but it doesn't really matter. N by n is typically fine. And I have some other vector B in Rn. And I draw a sample from this. So I draw a sample x, and then I form y being equal to ax, little x, plus b. This variable, so after this transformation, y here will be multivariate Gaussian with mean b. That sort of seems obvious, right? Because I'm taking all my mean 0 variables and I'm adding some term b to them. That should make their mean b. Again, b here is a vector. I'm adding b to them, so their mean should obviously be b. But importantly, the covariance here is A transpose. So what the covariance really means in some sense is if I can decompose the covariance to be a product of two matrices like this. And it turns out the covariance is always what's called a positive semi-definite matrix. And so you actually always can write it out like that. Then you can think of what this is really saying is that samples from that distribution are like samples from an independent standard normal distribution, where I then multiply it by A and then add the mean B. So that's kind of what random normal variables are in higher dimensions. And it's very useful for sampling from them, because we know the call for constructing, we know the rand n call, and so this is how we can actually sample from them. So let's take a look. Here I generated 1,000 samples from a random normal variable. This is a random variable in two dimensions here, x1 and x2, where the mean was 3, 4, 3, negative 4. So this mean here, the center is at 3, positive 3. The center on the y-axis is at negative 4. I'm just picking random numbers here. And the covariance here is equal to this matrix here. Now this says a few things, actually. It says a few interesting things. One thing it says is that the variance of the x1 variable. Remember, the covariance is the matrix of all possible variances, right? So if I just consider the x1 variable from this distribution, and I look at the variance, we know that that variance is going to be equal to 2, right? So this variance here, the average amount we vary here from our center is equal to 2. In fact, the average amount we vary from our center in that direction, so the average amount we vary from 3 here, measured by that variance term, is equal to 2. Similarly, in the y direction, the x2 direction, our variance there is 1. So we vary, according to that term, from that mean in that dimension by 1 on average. Or rather, the expected value of the distance between that and the mean squared is equal to 1. And what's interesting also here are these off-diagonal terms. So the off-diagonal terms capture how much covariance there is between x1 and x2. And if that number is high, that means that these two variables are very highly correlated positively. So this would be what it looks like for 0.5 being the covariance between x1 and x2. And you can see there's sort of a slight positive slope to these lines in some sense, or to these points in some sense. And what that means is that if I know one variable, I can make a better guess at the other variable because there is some correlation there. That contrasts with a situation like this, where there's actually, this is the same plot here, but now with the covariance equal to 0. Or sorry, the same distribution in every way, except that the covariance is equal to 0. And here what we actually see is that there's no relationship between x1 and x2, right? Knowing, if I tell you x1 is here, that will not help you pick what x2 is there. By the way, what I'm plotting here, those figures that I'm plotting there, are actually the sub-level sets of the inverse covariance. What I mean by that is those are essentially, if you look at the distance which you are of the inverse covariance, you can think of that as essentially being points in that. So these lines here are measures of distance according to the covariance matrix. I don't know how detailed I want to be here, but what it really means is that the distance, this quantity, x minus mu transpose sigma inverse x minus mu, that quantity is the same along those entire circles there. And so that's actually a good way of plotting these Gaussians, because it sort of shows how am I measuring how far away something is. And I'm actually measuring it exactly like this. This is what's something called a quadratic form. We're not going to worry too much about that. By the way, this is also, well, I don't want to get into this too much, but if we had this transformation here, then this thing would be essentially equal to, if the sigma is like this thing would also be equal to the 2 norm of A times x minus b. Sorry, A inverse x minus b, right? That would be equal to this thing. So this is sort of the distance between these 2 points in this, under this transformation of the matrix A here. But that's sort of the way in which that is a distance metric. But what's important here is that the red lines signify points of equal distance. In other words, because they're the equal distance, they're going to have the same probability. So those points are all points of equal probability along that, in that distribution. And so what you can kind of see is that these set of points are elongated in this direction, right? And so what this is saying is that even though that point sort of on the tip there is farther away from the mean than this point here, they have the same probability, because our probability, our distribution actually is more likely to have points that span kind of this direction than it is to span this direction. Okay, so this is the uncorrelated one. This is the one where the off-diagonal terms are all 0, meaning that if I am to know one point here, one dimension, it wouldn't really help me break the next one, because the distribution looks the same for all other settings for all values of x1. The distribution over x2 looks the same. These distributions like this are characterized by diagonal covariance matrices, right? There's no covariance between other terms. And that actually is the same as if you just sample n independent Gaussians along each dimension, because there's no covariance between the different terms. But we can look at sort of the other extremes too. We can kind of make here the off-diagonal terms are 1. It's getting more elongated here. It's 1.4. It's getting very, very stretched out here. And you can imagine, right, that in this representation, if I know my value of x1, say I know the x1 of some random variable is equal to negative or equal to 2, I'll have a very tight band in which I know what x2 should be, even though if I just look at the distribution of x1, it still has variance 2, right? There's still, as a whole, this still varies by 2. But if I know what the value of x2 is, it's a much tighter distribution than I would have otherwise. This will actually top out at this off-diagonal term being the square root of 2. That just falls out, in this case, from what it takes to make this matrix singular, essentially be non-invertible. And when the matrix becomes non-invertible, bad things happen. You can't do that inversion anymore, so you can get close to the square root of 2, but you can't actually hit it. Okay, and then if you have these terms being negative, which you can have, again, in this case, you could go all the way to negative square root of 2. That just gives you inverse correlation. So now they're still very correlated, these two variables, but the correlation runs in the opposite direction. In other words, sort of goes this way. Okay, I'm almost running out of time here, so I'm just going to try to finish up just the multivariate Gaussians before I get to anything else. And I'll say just only a few words here because this is actually also, just like those integrals, I mean, it seems apparent because we call mu the mean and we call sigma the covariance. That does not mean that these integrals are in any way obvious, right? They are high-dimensional integrals over n dimensions. Writing them out is a total pain. You need to use actually complex calculus usually to solve these kind of nicely. They're a total pain. So it's not at all obvious why this is the case, but I'm just telling you it's the case. Just like that, actually easier than that. This one is not as hard if you have certain definitions. But just like that, I'm going to tell you that the maximum likelihood estimates for these parameters are given by the following. So again, remember, maximum likelihood estimation is the following. We are given a collection of data, right? So we're given a set of points x1 through xm, x superscript 1 through x superscript m. And we want to estimate what are the parameters what are the value of the parameters that maximize the probability of the data that I've observed under those parameters, right? The way we do that is we take what's called the log likelihood. It is the sum of the log probabilities of all the data points under that model. We write that in term, and we think about that as a function of the parameters. So I write that as little l, mu, and sigma. And then I find the maximum value of that log likelihood, that L value, L of mu and sigma here. The way I do that is I take gradients, I set them equal to 0, and I solve for those. And I will tell you, if you do that here, what you will get is you will get the shocking expression that the mean is equal to the average of the data points, and the covariance matrix is equal to the empirical covariance. It is equal to xi minus mu, the outer product of xi minus mu times xi minus mu, average over your whole data. So I think actually these results kind of seem too simple. They actually kind of trick you in being too simple. They are not that simple, actually. Why is this? What's going on here? They're not that simple. But they are nice properties to have, and they make Gaussians really nice, and they make it easy to estimate Gaussians, all these kind of nice things. So we use them a lot. Before I go, well, I can show this next time. If you look at the slides too, I have essentially, if you take MNIST and you fit a Gaussian to all of MNIST, this is the mean digit. So this is if you average all of them together, you get this digit. This is the covariance. So here I'm showing like in the vector space. So all 784 pixels here. This is the covariance matrix in that space. It's sort of hard to see what it's actually doing here, but basically it means that there are some points that are highly correlated, some points that are not. But it's a little bit odd because we can't really think about these things as vectors very well. All right, so next time I'll get back a little bit to outlier detection, and I'll finish up or start talking about mixtures of Gaussians.